Hi, this is Dr. Habib Ahmed. Previously, I posted a video on the Silvaco TCAD simulation of perovskite solar cells. However, that video was a preliminary one. It was not optimized, and the efficiency of that structure was not great. So what I did is that I optimized the layer thicknesses of various materials in this structure. I optimized the doping concentrations, and I used more accurate material parameters for all the layers inside the perovskite solar cell structure, resulting in a really good efficiency of more than 25% for this perovskite solar cell. Well, you know that the maximum efficiency that has been achieved with perovskite solar cells is approximately 30%, which is close to a record. But those structures are based on materials in combination either with metal ammonium lead iodide or a combination of other perovskite layers, not just based on a single perovskite layer of metal ammonium lead iodide. This is a more basic structure. I optimized the material parameters, the layer thicknesses, and also I used more accurate material properties in order to get an optimal result that I can achieve from the same structure. We know that in a solar cell, the input is light energy and the output is electrical energy. And with the recent progress in perovskite solar cells have developed more rapidly. Perovskite solar cells have some really good properties. For example, they have a large absorption coefficient, which means that perovskites can absorb light more efficiently as compared to other materials. Secondly, perovskites have high electron and hole mobility, so their diffusion lengths are larger, which means that when you generate electron and hole pairs inside the perovskite solar cell, they are not going to be recombined right away. They can travel to the anode and cathode contacts, get collected at the opposite electrodes, resulting in contribution to current and voltage. Third, and more importantly, perovskites are cheaper as compared to a lot of other conventional inorganic materials. So it's a futuristic technology, not like the far future. In the near future, we will see a lot of perovskite solar cells and solar panels in the market. This technology is really trending right now. Now, perovskites are actually a combination of organic and inorganic layers. Its formula is ABX, where A represents large cations, for example, metal ammonium. B represents metal cation, for example, lead. And X represents anions such as chlorine, bromine, and iodine. In this structure, I have used nickel oxide as a whole transport layer. Nickel oxide has a band gap in the range of 3.2 to 3.8 electron volts, and I have used a band gap of 3.5 electron volts for the nickel oxide layer. Similarly, zinc oxide has been used here as an electron transport layer. Zinc oxide has a band gap of approximately 3.3 electron volts. Both nickel oxide and zinc oxide have high mobilities. They have good transmittance to the visible light. We need good transmittance for the nickel oxide layer and also for the zinc oxide layer, so that light can easily travel to the active layer, which is our perovskite layer, or in this case we can say to the metal ammonium lead iodide layer. And also, nickel oxide has a really good electron blocking property layer, or you can say it's a good hole transport layer. Similarly, zinc oxide has a really good hole blocking property, or you can say it's a really good electron transport layer. With that being said, let me walk you through the code. So as you know that the font size inside the deck build environment of Silvaco TCAD is not good, and I don't really see any option to increase the font size. So I have copied the code inside a Microsoft Word document as well. We start with Go Atlas. Then we define the meshing. My structure is running from 0 to 1 micrometers in the x direction. As you can see over here, running from 0 to 1 micrometer. Similarly, it's running from 0 to 0.38 micrometers in the y direction, or you can say it's running from 0 to 380 nanometers in the y direction, which is visible from here as well. We define the meshing such that we introduce denser meshing at the interfaces and sparser meshing in the bulk regions. So like for example, if we move to the next structure, we see here that we have denser meshing at the interfaces and less dense meshing in the bulk region. So that's how we optimally utilize the meshing for our structure. You know, I'm not really gonna go into the details of the meshing because I've gone over the meshing so many times in my previous videos as well. So I'm just gonna focus on the more important parameters related to the simulation of the perovskite solar cell. Then my region number 1 is a user defined material. I call it glass. Its group is insulator, and its dimensions are 0 in the x direction and 0 in the y direction. So it does not really have any thickness. And then my region number 2 is indium tin oxide, running from 0 to 1 micrometers in the x direction and from 0 to 0.060, or you can say 0 to 60 nanometers in the y direction. As you can see from the structure, it's running from 0 to 60 nanometers in the y direction. Similarly, region number 3 is nickel oxide, and nickel oxide is not a built-in material inside Silvaco TCAD. So I have set it as a user-defined material. And I've already posted a video on how to include a new material in Silvaco TCAD. So I'm not going to go over the details of how to include nickel oxide into Silvaco TCAD. You can go over that detailed video. But here I've introduced it as a user-defined material. Nickel oxide is running from 60 nanometers to 100 nanometers, as you can see in this structure. Here is the reference chart. Nickel oxide is the green layer, running from 60 to 100 nanometers. Similarly, methyl ammonium lead iodide is my region number 4. Once again, it's a user-defined material, running from 0 to 1 micrometers in the x direction and from 100 to 300 nanometers in the y direction. As you can see, it's running from 0.1 to 0.3 micrometers. And here is the reference chart for this structure. Similarly, I have included zinc oxide as region number 5, running from 300 to 340 nanometers in the y direction. 300 to 340 nanometers in the y direction. Then my region number 6 is aluminum, running from 340 to 380 nanometers in the y direction. So here is aluminum running from 340 to 380 nanometers. I have set indium tin oxide as an anode. Its coordinates are our dimensions are 0 to 1 in the x direction and 0 to 60 nanometers in the y direction. So you can see in this structure, indium tin oxide is my anode, indium tin oxide is a good transparent conductive material. It has good transmittance, so it can act as an electrode and also allowing the visible light to pass through it without significant absorbance. And I have set the aluminum layer as cathode in my structure. Then I save the structure with the solar.str. I run Go Atlas once again. I import this solar.structure file into my code. I have set the doping concentrations for different layers. For example, let me move it to the side. My carrier concentration is 2 × 10⁻20 for region number 2, which is ITO. It's 2 × 10⁻19 for the nickel oxide layer. Nickel oxide, by the way, is a p-type material inherently by nature, and we can increase its doping to higher levels as well. Similarly, my doping is 1 × 10⁻15 for region number 4, which is the perovskite layer, the metal ammonium lead iodide layer, and it's 1 × 10⁻19 for region number 5, which is the zinc oxide layer. And I've introduced hole concentration for the nickel oxide layer and electron concentration for the zinc oxide layer. Then I've introduced the material properties for indium tin oxide. Here is the band gap. Here is the band gap. Electron affinity, permittivity, density of states in the conduction band, density of states in the valence band, the electron mobility, the hole mobility. SOPRA represent files, built-in files inside Silvaco TCAD, which have the optical properties of materials. For example, ITO2.nk has the optical properties of indium tin oxide. So N over here represents the refractive index and K represents the absorption coefficient. And these materials do not have a single refractive index and a single absorption coefficient. Their refractive indices and absorption coefficients vary versus the wavelength of the visible light or the input light, you can say. So these are actually files which have a range of values for the refractive indices and for the absorption coefficients versus wavelength. Then I have set the electron and hole lifetime for indium tin oxide as well. Similarly, nickel oxide is a user-defined material. Here is the band gap, affinity, so many other parameters, electron and hole mobility, and its optical properties match with zirconium oxide. So I've included the optical file for zirconium oxide for nickel oxide. And then here are the recombination lifetimes. Here is the active layer, the metal ammonium lead iodide. Once again, this is a user-defined material. Its band gap is 1.5, suitable in the visible light range. Affinity, permittivity, density of states in the conduction and valence band, electron and hole mobility, which are decent values for a perovskite material. However, we do not have, since it is a user-defined material, so we don't have the optical properties of metal ammonium lead iodide inside Silvaco TCAD. So what I did is that I created a file with this name which has the optical properties for metal ammonium lead iodide, and it's in the current directory over here. In the description you can say this is an NK file. When we open this file, we have 11 triplet entries into this file. The first entry represents the wavelength, the second entry represents the the refractive index, and the third entry represents the absorption coefficient. So we have these optical properties in the range of 0.3 to 0.9 for the metal ammonium lead iodide material. And the program automatically interpolates and extrapolates values in other ranges for the visible light spectrum for the metal ammonium lead iodide layer. And then this perovskite has good electron and hole recombination lifetime. Similarly, I have defined the properties, material properties for a zinc oxide as well. Once again, it's a built-in material inside Silvaco TCAD, but we still don't have the optical properties of zinc oxide inside Silvaco TCAD, not in the current version that I'm using. So what we do is we make an NK file, like I've generated one over here. Zinc oxide.nk, which has the optical properties for zinc oxide, and we call this file into Silvaco TCAD using the command index.file. And similarly, we include the optical properties for aluminum as well into the code. Then we include different models into our code. For example, bipolar, Fermi, Shockley-Red Hall, field dependent mobility, concentration dependent mobility, OJ recombination, the optical properties, for example, the optical intensity parameters, and print gives us the runtime output in Silvaco TCAD. Then we include a method for the solution of our devices. I'm using Newton as a method, but we can also use other methods, for example, Gummel and block. Gummel gives us linear convergence. Newton gives us quadratic convergence. Newton is more suitable for this current simulation. And then in order to look at various output parameters, I'm using the command of output. So I want to look at the optical intensity, the conduction energy level, the valence energy level, polarity charges, electron and hole mobility, recombination parameters, radiative, OJ recombination, and permittivity, etc., those kind of parameters. And then this backslash over here represents that we are that this is actually part of this code. So we are moving to the next line for the same code. Then I have set the anode work function to 5. My anode is indium tin oxide, which has a work function close to 5 electron volts. Similarly, my cathode is aluminum, which has a work function of approximately 4.3 electron volts. Then I save the structure under thermal equilibrium and plot the structure. Now I want to look at the current voltage characteristics of the perovskite solar cell under dark conditions. So I sweep the anode voltage from 0 to 1.3 volts with a step of 0.01 volts. Similarly, I also want to look at the IV characteristics of my perovskite solar cell under light conditions. So first I need to illuminate the device. So we need to assign an optical intensity to my perovskite solar cell. So this is beam number 1, and I am using AM 1.5 spectrum. The solar spectrum runs from 0.2 to approximately 3 micrometers, and AM 1.5 represents the standard test conditions, which are 1 kilowatt per meter square light intensity, room temperature, and 48.2 degrees angle of the sunlight to the zenith, to the vertical axis, and I'm shining it slightly above my structure, so like around here, with an x coordinate of 0.5 and y of -1, so around here, at an angle of 90 degrees. Then I illuminate the device. I enable the light intensity using this command solve B1, and B1 is equal to 1 represents 1 kilowatt per meter square light intensity, which corresponds to the standard test conditions. But we slowly ramp up the input light intensity from 1 milliwatt per meter square to 10 milliwatt per meter square to 100 milliwatt per meter square to 1 kilowatt per meter square, in order to avoid any convergence problems. And then under light conditions, and then I create a log file, and I sweep the voltage from 0 to 1.3 volts under light conditions, and I plot the dark and light IV characteristics onto the same plot. I plot the structure under light conditions here. And now I want to look at various performance parameters of the solar cell, various figures of merit of the solar cell. So I initiate this file solar_light.log, which has the IV characteristics of the solar cell under light conditions. Here I've created a log file over here. And from here I calculate the short circuit current density, which would correspond to the y-intercept of the IV characteristic. Similarly, I calculate the short circuit current density in milliamps per centimeter square. For milli, I multiply 1 10 to the power of 3 to convert it from amps to milliamps. And then per centimeter square, the area of my device is 1 micrometer by 1 micrometer. Let me tell you how. This is really crucial. So in X direction, my device is running from 0 to 1 micrometer, and light intensity is incident onto the top surface. But actually this structure has a third dimension as well, which we are not able to see over here right now. By default, there is a Z dimension in Silvaco TCAD codes as well, even if we are working with the two-dimensional structures. And by default, the value of the Z dimension is 1 micrometer, unless you set it to some other value for which we have the luxury. So the area of this structure is 1 micrometer by 1 micrometer. 1 micrometer in the X direction and 1 micrometer in the Z direction, where the light intensity is incident on the top surface in the XZ plane. So, and then 1 micrometer by 1 micrometer means 10 to the power minus 4 centimeter into 10 to the power minus 4 centimeter. Take it to the numerator, it comes out to be 10 to the power of 8 centimeter square. So this is the area of the device, and this is the current density in milliamps. Multiplied with 10 to the power of 3, it comes out to be milliamps per centimeter square. We get the open circuit voltage, where the x-intercept is 0 for the IV characteristic. Similarly, we calculate, we look at the power curve, and we calculate the maximum power by multiplying the maximum voltage with the maximum current. As we know, in the light IV characteristic of a solar cell, there is a maximum voltage and maximum current point corresponding to the maximum power point. Similarly, we can calculate the fill factor, which is equal to maximum voltage times maximum current divided by open circuit voltage times short circuit current into 100. Similarly, our efficiency is going to be the output power divided by the input power. The output power is electrical power, which is the multiplication of the maximum current and maximum voltage. And similarly, the input is optical power, which is 1 milliwatt per centimeter square. 1 kilowatt per meter square, or you can say 100 milliwatt per centimeter square, or you can say 0.1 watt per centimeter square. And then its area is 10 to the power is 1 micrometer into 1 micrometer, you can say 10 to the power minus 4 into 10 to the power minus 4 centimeter square. Take it to a numerator, it comes out as 10 to the power of 8 into 100%. So this is going to give us the efficiency of the perovskite solar cell. And then we plot the power curve as well. Now we start with another block of the code. So we run Go Atlas once again, and in this block I want to plot the internal and external quantum efficiency and also the solar spectrum. So we enter the material properties once again. We define the work functions. We initiate a beam. We want to look at the output parameters, and we introduce models. I created a log file with the name of solar3.log, and then I want to look at the spectrum in the wavelength range of 0.05 to 1 micrometers, or you can say 50 nanometers to 1000 nanometers with a wavelength step of 0.05 micrometers or 5 nanometers. So then I plot this spectrum. Then I initiate this spectrum solar3.log, and from here I want to calculate the internal quantum efficiency and the external quantum efficiency at different wavelengths. Finally, I plot the internal and external quantum efficiencies, and finally we quit the program. So now it's time to run the program. Here is the structure of the perovskite solar cell under thermal equilibrium. Right click on the structure and click display. This icon gives us the meshing on this structure. As you can see, the meshing is denser at the interfaces and sparser in other regions. Similarly, we click on this icon in order to see the electrodes, the anode and cathode across the structure. So as you can see, my anode is the indium tin oxide layer and the cathode is the aluminum layer. Similarly, if I go to display and click on contours, we go to define contours, and we can look at the absolute net doping across the structure. So here is the reference chart. So as you can see, the dopings are high in the zinc oxide, in the nickel oxide. This is the nickel oxide layer, and this is and also in the zinc oxide layer, and it is lower in the methyl ammonium lead iodide layer, which is the perovskite layer. So we kind of have a PIN kind of structure here. Disable, looking at the dopings here. Similarly, let me check the progress of the code so far as well. So right now it's running the sweep from 0 to 1.3 volts under light conditions. For the structure under thermal equilibrium, we can also look at some other parameters by drawing a cut line. So here is the doping profile across the structure, and I'm more interested in looking at the energy band diagram, because energy band diagram is really crucial. If you understand energy band gap, if you can perform energy band gap engineering, you can design devices based on that. So understanding energy band gaps and energy band diagrams is really crucial. So I click on, let me minimize the other windows as for now. You want to look at the conduction energy level, the electron quasi-Fermi level, valence energy level, and hole quasi-Fermi level. And I hit apply. So here is the energy band diagram. On this side we have the nickel oxide layer, and this is the indium. This corresponds to the indium tin oxide layer, and indium tin oxide over here is a contact. Then this one over here corresponds to the nickel oxide film, which is p-type. Since the Fermi energy level is close to the valence band, so here we can infer that this layer is p-type. Similarly, this layer on the right is zinc oxide, which is also obvious from the fact that the Fermi energy level here is close to the conduction energy level. Similarly, in the middle we have methyl ammonium lead iodide, which we consider it as an I layer because the doping concentration in this layer is really low. And this layer on the right is the aluminum contact layer. Then I'm gonna minimize this one over here. Now we want to look at some other properties. For example, here are the IV characteristics of the perovskite solar cell under dark and light condition. The green one corresponds to the IV characteristic under light condition, and the red one corresponds to the IV characteristic under dark conditions. So the intercept of this light IV curve on the y-axis corresponds to the short circuit current density, and the intercept of this on the x-axis corresponds to the open circuit voltage. So the open circuit voltage is going to be around here, around 1.1, around 1.1 you can say, or slightly more than 1.1, close to 1.2. Similarly, short circuit current density is gonna current is gonna be around 3 into 10 to the power minus 10 amps. We can also look at the power curve, which is the product of V and I, and we see a maximum power around 0.85 volts. Similarly, we can look at the structure under light conditions as well. So for this structure, if I right click on the structure, then click on contours, go to define contours, and I want to see the photon absorption rate for the structure. Then hit apply, click OK. So we see over here, looking at the reference chart, that the photon absorption is high in the active layer inside the perovskite layer, and it's really low in the remaining layers. Similarly, we can also look at the photo generation rate inside different layers. We go to define contours, and here is the photo generation rate. Hit apply. So here is the photo generation rate inside different layers, as you can see from this structure. The nickel oxide is a really good layer because it allows the visible light to pass through it. So it has a good transmittance for the perovskite solar cell. We can also see by using cut line, we can also see the exact curve for the photo generation rate and for the photon absorption rate as well, as you can see over here. This region corresponds to the nickel oxide film. This region corresponds to the perovskite solar cell layers. As you can see that this layer has a really good photon absorption property. And also we can see that here we can further increase the thickness of this layer because it's still exponentially trending down. So we can further increase the thickness in order to achieve more optimal performance from this perovskite solar cell device. I also want to see the energy band diagram of this structure under light conditions. So for that purpose, I disable the photon absorption and I enable the conduction energy level, valence, electron, quasi-Fermi level, and hole quasi-Fermi level. And I'm going to disable these asterisks. So now here is the energy band diagram of the structure under light conditions. When light is incident on this structure from this direction from the nickel oxide layer, it's going to be absorbed predominantly inside the perovskite layer, resulting in the generation of electrons and holes. Now electrons have a tendency to move to the right. If they move to the left, there is an electron blocking layer over here. This is a big barrier. The nickel oxide acts as an electron blocking layer. However, the zinc oxide layer facilitates the transport of electrons to the right electrode, which is aluminum. Similarly, this zinc oxide acts as a hole blocking layer. So when electrons and holes are generated, the holes, if they travel towards the right, there is a big barrier for holes because holes tend to move to the top of the valence band. So, but if they travel to the left, they can easily get collected by the anode contact. So the nickel oxide acts as an electron blocking, or you can say as a hole transport layer. Similarly, the zinc oxide layer acts as an electron transport layer, or you can say a hole blocking layer. We can also look at the performance parameters, or in other words, you can say are the figures of merit for the perovskite solar cell. So if I click on this icon, we see the short circuit current density, which is around 29.55 milliamps per meter square. Our open circuit voltage is 1.13. The maximum power is 2.52 10 to the power minus 10. The maximum voltage is approximately 0.9 and the maximum current is 2.80 10 to the power minus 10. The fill factor is 75.5. So this can further be improved. It's not on the it's good, but it's not great. And our efficiency, as you can see, is approximately 25.25%, which is really good. So these are good figures of merit for the perovskite solar cell. Similarly, we can look at the spectral response of this perovskite solar cell. Here we click on optical wavelength as an x-axis, and cathode current as a dependent variable. So here we see the visible the spectral range. So you can say its spectral range is from 0.2 to approximately 0.9 micrometers. We can also look at the internal and external quantum efficiency of these solar cells. So here is the internal quantum efficiency close to 1, and here is the external quantum efficiency. The external quantum efficiency is generally lower than the internal quantum efficiency because of several non-idealities, several reasons. For example, because the energy of the input light could be smaller than the band gap of the semiconductor. Similarly, when we generate electron-hole pairs inside the semiconductor, not all the generated electron-hole pairs are collected by the respective contacts. Some of them get recombined in the process. Similarly, there could be reflection of light from the top surface, incomplete absorbance, shading by the contacts, non-ideal collection at the contacts, and so many other reasons. So because of those reasons, our external quantum efficiency is always lower than the internal quantum efficiency. So that's it as for now. I hope this video was informative and useful for you. Till next time, take care. Adios.